Good morning, everyone. Hello. Glad to have you all here this morning. So to introduce myself, I'm Carla. I'm the marketing manager here at FuseForward. And this is our first event of the year, and it's the 10th webinar in our remote control series. So we started this series back when, we had to cancel some in-person events at the beginning of COVID. And it's actually been great to have, everyone join us, see our audience grow and, open this up to people in a wider group around the world. So I'm really looking forward to today's webinar. The topic is the role of digital twins in asset lifecycle management. And presenting, we have Mark Dam, our CTO, and he is a regular on this series. And I'm really looking forward to today's topic. There's been a lot of interest in this, and so it's exciting that we're presenting it. So I'm not going to take any more of your time. I think we're all here to hear from Mark, so I'm going to hand it to him. Over to you, Mark.
Thank you very much. So you want to hear from me again. Geez, I do a lot of these presentations. So it's been an interesting time in the last couple of months as we've been hearing some of the challenges on the electric grids throughout the world, as well as we've had some very good remote control series over the last couple of months as well from some of our partners in the campus arenas, where we've been talking about some of the work we've been doing with Ryerson University out of Toronto. Today, I'm going to share with you a little bit of the role of digital twins in asset lifecycle management. Now, what's interesting on this is some of the work around asset lifecycle management. I remember doing presentations on asset lifecycle management, optimization plans around that way back about 15 to 20 years ago. And I always look at it and say, has the world changed? What has changed? How much have we learned? What are the new standards in place? Are there ways that we have our inventories? Are we ahead of the curve yet? Or do we still have the same problems we had 15 years ago? So I'm gonna talk a little bit through that today, share you some of my experiences over those years, as well as give you some background into what the digital twins are and how they can be applied to your asset lifecycle management challenges and opportunities moving forward. As we move forward, we always like to start off our series with a poll. The poll this time is one of, and Carla, is it sharing? I'm assuming it's sharing now. What I would like to see is, what are your greatest asset management challenges? Is it maintenance of your assets, extreme weather conditions like we're having around the world in various places, aging infrastructure, things are falling apart all the time? Are you having funding shortfalls? Do you have enough money to do anything? All of the above? Or is there other things that you're dealing with? And then a second question we have is, do you have an asset management strategy in place in your organization? Yes, no, or you don't know. So I'll let you guys open it up to the voting. Gives us a little background as to who we have and and what our challenges are and what we can explain as we go through the day today.
Yeah, so it looks like answers are coming in. I'm just going to give it a few more seconds here because I can still see a lot of responses. It's interesting. It's sort of balancing out across all of these challenges. I am going to end the poll now. So we have greatest asset management challenges, maintenance at 46%. Makes sense. Closely followed by aging infrastructure. And then we have all of the above. So
which
challenging for everyone.
Doesn't surprise me at all.
Yeah. And then we have 51% with an asset management strategy in place.
So there is actually, that's a big change from what we talked about over the last 15, 18 years. I know asset management strategies back in the early 2000s, we were just doing super sessions with the American Public Works Association as an example, and some of the energy organizations, and actually developing for them asset management strategies. So good to know that at least a lot has changed, and that we are starting to see at least that whole technique and that knowledge of ISO 55000 and the whole areas of doing asset lifecycle management now being incorporated into organization strategy. So let's jump into the content today, and let's talk a little bit about what we have and how we're driving. So I'm going to go back. This is my history. I remember back in 1998, a massive ice storm in the Northeast US. It froze the grid. You see here pictures where we actually had transmission lines and transmission towers falling down from all the ice on it. The Northeast US was basically frozen out with power outages rolling all across the grid. And it showed the interconnectedness of different grid organizations and how that happened. Well, interestingly enough, that was about, as we say, 20 odd years ago. Now, what did we happen in the last little while? Well, Texas has gone through the same thing. They're going through another crazy world right now where the Texas freeze, and we started having the grid failing again. What we've also got is the UK going through the same thing. The grid is creaking at the risk of blackouts right now in order to go and handle all of that. And then what we also have right now is we also have areas where we also have South Africa is crippling with blackouts as well. Sorry, that is my phone ringing because I am at home right now and normally I have all that turned off. So let's go through a little bit and let's learn and let's drive through what is some of the solutions to learning our lessons from all of these different opportunities. So the key thing that I started talking about 15 years, 18, 20 years ago now was asset lifecycle management. How do we come up, and I remember writing a whole series of articles on this, on how do we go through and manage the life cycle of an asset, not just strictly the maintenance of it, but what about the innovations related to the new capital programs? How do I look at going through and aligning my capital programs with my operations and maintenance? What should I be doing to go through and manage the upgrades and life cycles and decommissioning works? And how do I plan for that over the life cycle? So those are kind of some of the challenges. I remember back in the early 2000s, I was in Washington, D.C. with the Environmental Protection Agency, and they were looking and said, well, how do we go through and manage assets today? When we go through and look at the universities were teaching engineers how to go through and build new stuff, and they were always motivated to build new. They didn't want to be looking at the life cycle, so what they were doing was saying, well, let's just build the biggest and greatest thing we can do again. And then we started looking and said, well, over time, we have to change that. And part of what we need to be looking at is innovative new ways of looking at microsystems, things like smaller grids or self-contained grids, or we start looking at ways of going through and having resiliency in our water, wastewater, and energy grid structure. And how do we do that? So those were the kinds of questions that we were driving in the early 2000s. In the early 2000s, what we were kind of asking was, could we go through and implement new green technologies for energy generation, windmills, wind farms, solar systems, etc.? That was new then. Now, 20 years later, there is a lot of that component, but is it all full base load? Can it handle the base load requirements? Have we basically put in all the resilient infrastructure in that? Another part that came along with asset lifecycle management was looking at our inventories. Do we actually know all of the assets we have? Do we know the condition of the assets? Are we able to go through and look at the criticality of certain assets and then determine which ones we should be over servicing, which pump in a system is really critical versus which one is not as critical, so we don't need to maintain as much? And we start getting into different maintenance strategies like reliability-based strategies, run-to-fail strategies, predictive maintenance programs, preventative maintenance programs. So part of that gets us into the point is like we start looking at our inventories, we start looking at criticality, we start looking at risk that we want to drive. And one of the things that we started to see was we started creating this whole area of a maturity model. And it wasn't one of organizations. In some cases, we had certain organizations say, you know, where we are on the maturity level is we're doing a lot of reactive maintenance today. And there was a lot of studies put out by the engineering firms and research organizations that said that a reactive maintenance program is anywhere between 7 and 10 times more expensive than trying to get into a proactive or a preventative maintenance program. So there was that whole area of maintenance of having to try and drive that. But in order to run a preventative or a predictive maintenance program, you needed data. So we all started to go through and implement asset management systems, started to collect the inventories, and started to go through and put together recurring maintenance programs to go and drive that together. So the interesting challenge we had was that we always thought it's like, well, I'm going to move from reactive maintenance and I'm going to get to predictive maintenance. But the way I like to describe this is a stepping stone. There are certain assets in your portfolio that you want to do reactive maintenance on. You want to run to fail. If you've got a valve somewhere that is just it's an old piece of equipment and it really is not part of a critical operating component of your infrastructure at all, you may sit here and say, well, the cost of sending a crew out to go through and maintain it is not worth the time it's going to take for us to do it. And we already know that 2 years later, we're going to run a major rehabilitation program along the whole system. So let's just let it run to fail. And if it fails, we'll go and fix it, or we'll kind of band-aid it until such time as we basically go through and replace it. So what we start looking at is this program where we start looking at reactive maintenance, preventative maintenance, and predictive maintenance. And we start looking at our asset inventories and we start saying it's always a mixed strategy. We apply some of the assets that have high criticality, high risk. If they fail, we want to run them on a predictive maintenance program. There's other ones that are part of our standard normal bell curve model. We want to run them on a preventative maintenance program. Other ones are not critical at all. They're run somewhere else. They don't impact service levels at all. We run them on a reactive maintenance and we basically go and fix them if they fail. But as we start moving more and more into the world of full cost analysis, we start running into things like asset lifecycle management. And the challenge that we run into in asset lifecycle management is we need to balance off things like cost. And I was listening to the Texas freeze here, and I was monitoring all the things that were causing the systems to fail. And here's an interesting fact. A lot of the facilities and new energy generation plants, because they're private sector, are all built and they were planning for major heat waves, not a cold wave. So what they were doing is, and a lot of their cost to capital calculations, because they're private sector organizations, they're looking at cost to capital over a 5 to 15-year window, not the age of the infrastructure. So if any of you are asset managers, you know that a lot of our infrastructure is long-lived. What does that mean? It means it's 15 to 50 years of life. A bridge is 50 years plus, okay? And when we start dealing with assets that have long lives to them, we have to then basically, the cost to capital calculation is not part of the equation here because we don't have a way to analyze the long-lived cost of capital, i.e. we don't borrow money on the markets at an interest rate that everybody can guarantee that that same interest rate is going to be there in 50 years time. It goes up and down, up and down, up and down. So when people are borrowing money on the bond markets, they're usually looking at it on what they can do in a way of a 5 to 10-year window on a bond basis. Okay, so that's part of our challenge then when we start looking at things like asset lifecycle management. Because what we want to do when we're dealing with asset lifecycle management is we want to be looking at the cost of installation and acquisition and commissioning. We want to look at the maintenance and operating costs. And we also want to look at any sort of major upgrades that we have during that life, which is not 5 years, but the 50 years. And so you've got these peaks and valleys of spend, and then you have another one where you have a big spike for rehabilitation, and then it goes down and your maintenance is much level and your operating costs are very low. And then you have some other ones, they start creeping up and they cost more. Now, in all of that, it becomes a very complicated equation, especially when we're looking at hundreds or thousands or millions of parts and assets in a portfolio for an organization. And so we've started to look and say, well, how do we simulate and how do we go through and use different decision support tools to help us? And that's where these digital twins come into play. So let me share with you now, as we jump into that, how we can move from our traditional approach, where we've now been looking at this whole 3 levels of maintenance programs that we've been learning how to do. We now are incorporating these life cycle analysis decisions into our asset management strategies. But how can we now use different sets of data and digital twins and support tools to help us do that? So let me jump into the details. So first off, what's the future look like? So one of the things I look at is I can start looking at collecting lots and lots of data for my pumps, as an example. I can go through and put a vibration sensor that used to be $100 or more on every pump now for $5. And that gives me real-time data of how my pump is pumping. And if the vibrations are getting out of sync, it says I might have a problem with the bearings. I might need to go through and do a maintenance job. Now, what's interesting is when I was working the oil and gas patch, we were doing vibration analysis on all of our critical infrastructure back in the late 80s. That is one of the key things that we're doing. And we were spending millions and millions of dollars, but we were dealing with oil. And what the problem was is that if there was one leakage from a pump and a pump failed, it was costing the pipeline company millions and millions of dollars because they had a committed contract to go and move it from point A to point B in a certain time window. So there was an economic incentive. When we're dealing with water and other things, it's not as much of an economic incentive. But now that the cost has come down, we have more and more data available to us for sensoring. And sensor data allows us to go through and now look at portfolios and look at different ways of getting real-time condition assessment of our assets. That means that we're able to monitor them. And we're able to go through and say, okay, here is the current state. And you can monitor the state over time with an IoT sensoring network. Well, what else now? Once you've got that IoT sensoring network, you can then also start looking at, we now know, and we use CAD drawings. We have GIS systems as well as part of our enterprise asset management systems. Those provide us with a way to visualize now that IoT data on top of a drawing set. And the drawing set is not paper, it's actually in the computer now, and it's part of those GIS drawings with multiple layers, or it's part of a CAD drawing set if it's a pump station or a transformer station. Now, once you've got those two pieces, then what happens? Well, there's this whole buzzword around the world today called machine learning and artificial intelligence. Well, really what we're talking about is we're talking about using computers with mechanisms where we have rule sets that can basically take all of the sensor data, overlay it on top of all these 3D drawings, and then basically start applying advanced analytics capabilities to it, i.e. using data science to go through and start saying, if I have all of these things, show me the behavior, try and predict what the behavior of this is. How's this example? Give me an example of this. That's what they do when you go into Amazon and you start going through and saying, I want to buy this. Or it's not just you, or somebody from your Facebook team or your family starts buying something and they start creating and saying, well, if they look at it, then I want to start targeting all these other people around you, and they become recommender systems. That's part of this whole area of advanced analytics, okay? So I don't want to get into a little bit, but let's go and bring this now down to the real world of the digital twin. And what is the digital twin and how can we apply it to this? So the way I like to describe it is I always do a little bit of, I'm not a gamer by any means, but because I have kids, I've always go through every once in a while and I pull up a game and I say, what are you playing? Can you show me? I want to see. Why are you being addicted? And of course, the addiction part is the scary part. So what I do is the first thing that's kind of always kind of tweaked me was SimCity and Second Life. SimCity and Second Life are two of the first simulation tools that we had from the gaming world that started to show us the real world, or at least a simulated version of the real world. So they use a gaming engine underneath, the Unity gaming engine or the Steam gaming engine. There's a couple of key ones out there that provide a way where you basically create a 3D model of something like a real world or a fake world, and then you have what we call agents interacting with it, and that's what a gaming engine does, okay? So SimCity is the first example of that. Well, that kind of says, well, how do we go through and take now what we've done in this simulated gaming world and apply it to the real world? Well, instead of going through and just strictly taking something like the virtual Minecraft type of model, we start creating physical 3D blueprints, real world connections of all the systems together. We take our GIS drawings, we convert them in, and we start creating the flow patterns that go with that. And we start putting the maps with a real world virtual simulation of what's going on. Okay. So then we start looking at it and say, well, where's this coming from? Not only are we monitoring what's going on, but we can then use that digital twin as a mechanism to simulate future design. So we can start looking and say, well, to go and build one of these new kind of drones, we actually simulate and do that in a virtual world first, okay? And that's the digital twin. So let me give you an example. This picture right here, this is part of the work that we're doing with Ryerson University in Toronto. So we've been building out and creating 3D blueprints of the buildings there. We've been installing and pulling in sensor data from all of their real-time control systems. And we're starting to put this on top so we can see what's going on inside their environment. And then what happens is we can then start looking at 3D and future works. So this diagram that you see here, this is an Autodesk Revit diagram. It's a 3D drawing of the actual building itself. And we have another remote control. If you want to look at this, we had one of our Ryerson partners, one of the researchers, do a good example and say, here, let's walk through and show you how we create these heat maps on top of these diagrams so we can see what's really going on inside that environment, but give it to you in a virtual world. So that's what the digital twin is. The digital twin is that virtual world today on how to do that. Now imagine for a minute you're a utility organization. Imagine that you have all of these, your whole system now is there, and you got a virtual flow analysis of all of your electric grid going or your water system going, and you can start looking and say, well, what do I want to do with it? Is there a way that I can help with certain decisions and questions that I have that I want to approach the digital twin to help me answer? So the way I look at it is digital twins are decision support tools. And that's what they are. They're not a replacement for the engineer or the operations technician. They are a support to them to help them handle this vast amount of data coming at them from all different directions and ask simple questions that we can use to have a decision support tool help us answer those questions. Now, I don't know people around here. I'm a sailor. I live in Vancouver. I've sailed from Vancouver to Hawaii. I've raced boats down in San Francisco. I've raced over in Hawaii. And I'm a big fan of America's Cup. So America's Cup, I'm not sure if anybody knows what America's Cup is, but I'm going to show you. The first world of America's Cup was sailing race boats. And over the last 20 years, we've gone from what we call monohulls to catamarans to these new foiling monohulls. Let me show you what I'm talking about. Okay, this is a little bit of America's Cup. And America's Cup is now a perfect example of a development class technology company where you have 4 companies right now, 4 organizations that are all using digital twins to go through and build these brand new high performance vehicles. Now, they're similar to a Formula 1 race car. But I got to tell you, you've got people going here, and I don't know if you've ever been on a boat and been thrown off a boat and landed in the water. It's pretty hard. And if you're underneath one of the sails, you can actually drown. So it's unlike Formula 1 where you get on fire. These ones are, you end up underneath the water. So let me show you a little video. We got a little clip here to show you the power of a digital twin.
Racing is pushing boundaries, and the America's Cup is essentially a design race. If there's one thing that's going to win the America's Cup for us, it will be simulation. With tow tank and tunnel testing banned and no sailing of 2 AC-75s at the same time, we rely entirely on simulation to drive our designs. No old school anymore. The battlefield of the America's Cup has really moved into the virtual environment, and it will be the ability of the teams to accurately model and predict the performance of the yachts that will really make the difference.
So hopefully you've heard that. I noticed a few people might not have been able to see it, but we can share the link for this. The key thing that comes out of this, and let me kind of show a little diagram on it, is the America's Cup teams have gone from basically designing boats and creating one version of it to creating hundreds of them, creating a simulation of the boat itself where you have your designers doing this. So it's not a race anymore of strictly who's got the best sailing skills. It's a race of designers coming up with the best boat design and being able to test those designs in virtual environments hundreds and hundreds and hundreds of times. To build the boat that you see here, they've had to build a simulator. They had to build a digital twin, then they tweak it. And then they basically started off by building a micro version of it, putting it out on the water, censoring the stink out of these micro little versions of it, getting a lot of data, and then bringing it back into the virtual world again. And it got into a iterative design process of coming up with this new foiling boats. Now, I don't know about you, but I'll share with you my experience of boats. So I've raced boats. you know, big ones, 55 footers. The maximum speed we could go in the water was about 12 to 16 knots downwind. This boat right here, the New America's Cup, are going upwards of 50 knots in the water, planing. And that means they all wear helmets, they wear goggles, the water is blowing in your face. I can't even imagine the times that go along with this. So what we have here is they have sensors, and all of these devices have, and the boats themselves have a software system on board to control it, hydraulics to control it, and it's a mechanical, electrical, and a computer generated system that manage these boats. And they basically have what they call a flight controller now on a boat. Now that's an interesting challenge, but that's that whole world of now using a simulator and using a digital twin to help drive new designs and new ways of building systems. Now imagine for a minute that we can go through and do this and say, we want to go and play this and use the same technique for my systems. So as an example, we want to simulate all kinds of different crazy weather events. So one of the things that happened is one of the races recently on America's Cup, they were rounding a mark. The wind went from 4 knots, 7 knots, or sorry, I think it was around 12 knots to around 20 knots in 2 seconds. And that's what happened to the boat. It basically blew out of the water and it ended up crashing. Okay, but in a wind tunnel, you can't necessarily, you can try and formulate those, but a virtual environment helps to now do that. They probably didn't use all of those key events, but that's more and more where they went back to the drawing board. And I guarantee you the other 3 boats and everybody else went forward, and their design team said, what can we do to handle that scenario? And they wanted to model it and start tweaking other components on their systems to go and handle those events. Well, what else can we do? Well, we can look at virtual simulations at a fraction of the cost of the physical demo. So instead of building these systems, building a new boat, building a new power plant, building a new grid, we can simulate what a grid would look like. What if we were to go through and build an electric grid that were semi-isolated with microgrids all connected in, and we started looking at the cascading effects of failure of one over the other? Or is there a way that we can basically turn off the interconnections so if a certain event happens, it just clicks off and the microgrid stands by itself? That's the kind of things that we can do with the digital twin. All right, what about this? Well, and we can then start looking at cascading events. So with the digital simulation of everything, in our life cycle analysis of all the assets, we can look at all these different simulation events that we want to look at, and we can simulate them all. And what does that help us do? It helps us with emergency situations and planning for that. It starts handling disaster recovery because we've already simulated certain events. We know what we should be doing if certain things are starting to twick up. The recent Texas, they said they were 4 minutes away from having a total grid failure in Texas a couple of weeks ago. 4 minutes. So the question is how can we go through? That was an early warning system, but is there a way that you can build a grid that's kind of a little bit isolated to go and do that? So the way I look at this, and the questions that always come to my mind, are trying to balance cost versus performance and the risk that you're willing to take. And it's kind of like that whole balancing act of everybody in this decision. I can spend lots of money, okay? If I'm an independent power producer, I could spend a lot of money, but I'm not going to get the return on investment. So I want to spend enough money, but then I have this performance. If I want to keep the system up and 100% available all the time, you got to build in redundancy everywhere. If I'm willing to live with 99.95% redundancy, when performance degradation comes down, I don't have to spend as much. If I want to go down to 98% uptime, I can decrease my costs as well. But it's a balancing act. Performance, cost, performance, cost. Then the question comes in is how much risk am I willing to take? If I'm dealing with a water system and there's a challenge, there's a potential for contaminants getting into the water streams, am I willing to go through and challenge and basically handle the risk of people getting contaminated from contagions in the streams? All right, energy. Am I willing to handle the risk of a total grid failure? All right, what about buildings and campus environments? Am I willing to go through and have a building shut down because their HVAC systems and the air conditioning system is not working? All kinds of different matrices come into play when we're looking at these different decision models of cost versus performance versus risk, and how we're balancing those against our risk criteria. Now let's look at that a little bit, okay? So let's ask the questioner a little bit about cost. So when I think of life cycle cost analysis, I think of what the initial cost is. I then think of the servicing cost. I think of the preventative maintenance cost. I think of all the operations that's going on, and then the disposal. And the thing is we always sit here and our funding models are a little bit broken, because in some cases we can get capital dollars, but we have nothing to operate. My wife worked in the hospitals for many years. She could go and get from the foundations lots of money to put in new radiology systems. But unfortunately, there was no operating dollars available to run it. So there was no staff that could run it. So I could buy them, I can install them. But unless I had all of those people available to operate it, and I had the maintenance dollars to keep it going, and I could pay for all the electricity to keep it running, I didn't have enough dollars in place. So there's a pot of money for capital, there's a pot of money for operations, and then there's this third pot of money for maintenance. And the question is and they're different people. So we always have to look at it. And one of the things I think that we're starting to learn is we have to look at everything from the nature of life cycle analysis, okay? Now, I'm going to go through 3 examples a little bit here and talk about some specific use cases now of where the digital twin can help us understand cost, performance, and risk, and how we can use a digital twin to actually help simulate and model these kind of questions. If I replace part of my generating capacity with an alternative, what would be the impact on the power grid? All right, so that question kind of came to us. We've been doing some work down in South Africa over the years, and one of the questions comes in is, what happens if I go through and put in microgrids? What if everybody on their house had a solar plant? And what if they were able to go through and do the generation on their own rooftop? And do they have enough, and could they put the power back on the grid? Well, one thing we learned a little bit about the grid is that the grid requires us to go through and step up power and step down power. So the grid initially, traditionally, has been built on a one-way feed of power. Step it down from transmission line to distribution system to home-based system, you're stepping down the power. Well, as soon as we start generating at the home and we want to put it back up, we've got to step it up if we want to go and transmit it across, or it needs to be locally used. Well, that's a complicated decision right there, okay? Just being able to look at the impact of what it would take in our system if we were to take a segment or a neighborhood and say, this neighborhood is going to have its own microgrid. It's going to have its own geothermal system to generate some of the heat. I'm going to use some of the steam. I'm going to generate some steam and create a steam generation facility on one of my university campuses. And we're going to start changing the demand profile on that. How is that going to impact us? So the kinds of things that we may want to be looking at when we're looking at that grid and the grid interconnections is, all right, what's the cost of the alternative energy in extreme weather conditions? So if I've got a small little grid and it's a microgrid in a neighborhood, is it going to be built so that if it's really hot or really cold, it can handle the air conditioning systems, or it can handle the heating systems that are going to be turned on, i.e. demand at the end of the day or the morning, things all generate and turn on at the same time. And it becomes a load that has to be handled in that microgrid. Now, we do that differently at a transmission or distribution level. So that kind of gets us into a little bit of the cost question. But what about the risk? If I'm going to model this, what are some of the alternative energies that can be provided to power the grid? Do I want to be using basically some sort of a solar system in the homes? Or do I need a natural gas that can be powered up quicker? Or is it something that should be a base load and I need a base certain amount of power generated locally to keep the grid active, to keep it 60 megahertz in place so that it's able to go through and keep an active system in place? Then what about the performance? Is the grid able to go through and have a base load always on it? And if part of a microgrid came down because we're now going through and changing the grid characteristics, are we able to go through and use the performance and still handle all of these different gen sets and the way to go and dynamically generate and handle demand side management, or to actually what we call do power dispatch? charge up and get another power grid going, okay, or get a new generation capacity started. Okay, so those are all those questions. Now that's where a digital twin comes into play. If I have a whole grid of my system and I started looking at it, I can start going through and say, you know, I'm going to go and I'm going to create a simulated version of a new generation source. And I'm going to drop them in these different neighborhoods. And then I'm going to go through and say, now I'm going to go and have my bots or my agents go through and start generating new power supply requirements and power demand requirements. And all of a sudden, we start seeing the interactions and seeing where things may fail if we start creating different load profiles on the grid. So there's an energy example. There is one that we can look at. Now, of course, I'm not just in energy. I've worked in energy sector, but I've also worked with organizations that are running water systems. All right. So one thing I've learned about water systems, I had one client, 250 pump stations, about 200 separate engineering designs for a pump station. And that means a whole different set of pumps. Okay, no standard manufacturer. It was like whatever the design guys and the engineer firms wanted to build for that contract, they did. And it wasn't based upon a standardized inventory. It was whatever was done at that point in time. Remember I said earlier about engineers loving to build the new stuff? That's what they were taught in school. So they like to build new stuff and use the latest and greatest technology. So one of the things that we always look at, if I'm looking at a whole inventory of assets, is I want a little bit of standardization. Not one vendor, not one pump, but at least trying to get away from 200 to maybe 5. So that I can do spare parts optimization, so I can do things of looking at how the different pumps work, and I can start calibrating them all in similar ways. Those are the kinds of things that I want to be able to do. So the question comes in is, let's say I've started my whole inventory and I've got 200 and I want to get down to 5. How would I go through and what would be the impacts of the system that I would need to do in order to start deploying that? And would I be able to, what was the risk that I would be having? And what would be the cost I would have in order to go and drive that? So there's the challenge. How can a digital twin help us? So a digital twin for this will help us by modeling the implementation of the pump replacement costs, the pump replacement plans. So as an example, should I take neighborhood A, neighborhood B, and neighborhood C? And since the cost of rallying the crews is the most expensive, I want to basically organize around doing the pump replacements in those areas, but I've got to do them in a rolling window approach, because what I don't want to do, I still need to have water flowing to everybody's house. So I need to be looking at the flow patterns and looking at how I can pull out a pump station and still have water flowing to certain neighborhoods during that pump replacement cycle. So how do I go through and plan that? How do I go through and create a pump replacement plan that is cost effective to putting the crews in the right place at the right time, while still going through and making sure that all of the systems and all of the different pumps are being replaced in the system with the standard version? All right, what else can I be doing with this pumps? Well, if I'm going to standardize on a set of pumps, what's going to happen if I actually do find that one of the 5 that I standardized on actually has a fundamental design flaw? Okay, so this is something along the lines of the airlines. You look at the airlines, and if they find one design flaw in one of the aircraft, they say all types of that same one are grounded. We have to go through and ground them all until we figure out what that design flaw was, and then we come up with a replacement plan for it. So again, from a risk point of view, if we're going to look at the water supply and we're going to standardize on 5 different types, we want to basically look and say, can we model that? Let's go and model, and let's use our digital twin to go through and look at a failure. If we look at it and say, you know, this pump failed and it has this at certain runtime hours, we know that it's going to start having a failure cycle and it's going to start failing at 2000 runtime hours. All right, so what we're going to do is we're going to sit here and say, well, now let's look at all the rest of where those things are deployed, and let's start looking at the cascading effects of everything hitting the 2000 runtime hours or the 1500 to 2500 runtime hours, and what that would affect. And what would that mean to our service levels? And what would it mean to our customer base if we started getting a cascading failure of these specific devices and pumps within our pump inventory? All right, there's a risk. What about performance? let's say I wanted to go through and model the performance of the different pumps and the configurations. So one of the things I've also learned is configuration management is a big deal. You go into a power plant, you go into a water plant, we see vibration as a key thing that we use. And one of our historical ways of dealing with it was to look at harmonics to go through and try and tune different pieces of equipment. Okay, so part of what we want to look at is how do we model the performance of different pumps and pump configurations? If we come up with one, is there a way that we can work within it and start going in? If we found that we've got a new innovation, it was applied to a certain pump and we wanted to make it work and it worked well, how would we go through and apply it to all of them across the board? And what would be the cost savings we might see? And what would be the performance improvements we would get in trying to improve that configuration across all the pumps? So the digital twin now can be used to go through and model that decision matrix. All right, I got a third one. Okay, this is my last. Okay, and then I'll get into some summaries that come along with this, and hopefully people are finding and getting some value from all the different examples here. The asset lifecycle analysis this time is how can I perform a major capital upgrade to my system? So what does this mean? Well, the cost of going through and doing a turn down or going into a power plant or going into a water treatment plant and saying, I'm turning it off to do a major overhaul has a significant cost implication. And the shorter the duration and the more work we can stuff into that same window in the way of major upgrades or major maintenance, the better we are in the long term. So everything related to managing a major capital upgrade is a major activity for planning. And that's where digital twin can also help. So the things that we can look at here are, can we model the different steps and processes and basically simulate in the digital twin the steps that we're going to take in order to go and do that whole upgrade? So if I'm going to go through and say, you know, I got to turn off the whole treatment facility, or I've got to go and turn off the power plant, I have to go and remove the turbine blades, I have to go through then and put my crew underneath, and I want to go through and do a whole set of maintenance work around it while I'm replacing the blades, or I'm going into the water treatment plant and I'm going to go and do a complete flushing program at the same time I'm in there. Those are things that we can start to go through and model in the way of all the steps it would take, what crews need to be there on what parts of the day, what they could all do within those time durations, and how much of the parallel activities we can start doing. And we can start simulating those to make sure that we understand the cascading effects of those different decisions in that capital window. So the window could be a week, it could be a month. And what you want to do is when you're in it, you want to be planning and executing with succinct timelines and not have the drag out that you could potentially have if some unexpected events happened. So you can simulate the unexpected events and then come up with scenarios that would say, if this happened, then we're going to do this. And you can start planning for that and trying that in the digital world before actually jumping in and bringing down the system. The other thing you can do is model the downtime. And what would happen is if I did bring down, say, 1, 2, or 3 of my transformer stations, what would be the overall impact on the performance of the grid at that point in time? If I brought down 2, 3, or 4 of my pump stations, what would be the impact of the pressure zones within my water utility? Okay, so those are all those kinds of things that we can do under the risk and understand the performance of our systems there as well. And then the last one is, what can we do also to isolate and minimize our customer disruptions? And I think I've talked a fair bit about that already. It's kind of like we can also use the digital twin as the means to look and say, who would be impacted when I bring these different components of the system down? All right, there's my examples. Hopefully you've got a flavor that how powerful these digital twins can be. Do they take some time? So things that you start looking at overall, you can use them for things like asset health, looking at maintenance expenditure optimization programs. We can look at things for system resiliency analysis. We can do load analysis, customer profile analysis, load forecasting. We can also look at demand side management, including conservation for either water or voltage, or look at our demand profiles on an hourly, daily, and weekly basis. Okay. There was a question, are the existing digital twins vanilla configs that can be built for specific industries? Well, it may sound like there's a lot of work there, but here's a couple of examples, and this is what we're doing. One of the things that we have with the digital twins to help with some of these use cases is creating component libraries. So the way that we're doing this is we're not trying to build a digital twin of a system. We're trying to build component libraries for systems of comparable performance so that we can start creating and allowing our customers and our communities to start using those as plugins to kind of help them in their environment. So as an example, it's a pressure zone, and here's a sample pressure zone for a water utility with X number of customers attached to it. Here's how it typically performs. And it's the more we can build libraries of components, the more we're able to rapidly get these simulations going of our current systems without having to go through and do and oversensor our own environment. So part of what we come along with on this one is the benefits of the digital twin to asset management. So key things I look at is it gives you a full picture of your asset life cycle. If you're using it, you can try and do this yourself all the time, but you know, the digital twin is going to give you some at least decision support tools to help you get what would be done when I'm dealing with 1 million records, 1 million pieces of assets in about 150 to 200 different asset categories with different stages of their life and all of the pieces. That's what the digital twin can help you simulate. It's a lot of data for my brain. I can't handle all of that, but the computers can. And what we can do is we can ask them and say, what if, what if, what if? And we can start helping to get better answers around the full picture of our asset lifecycle cost analysis or asset lifecycle analysis. We can help to use digital twins to help us go through and anticipate events and be ready to respond. So it's disaster recovery, emergency preparedness, safety management. All of those areas are things that we can now use our digital twins for. We can minimize our asset purchasing for testing. Instead of having to go and buy new gear and try it in the field all the time, well, let's go and take a simulated version of one and see how it would perform in typical simulated environments. And again, we can get to the point where we say, instead of it being this broad, we can narrow down to the point where now we need to try it here because we're now ready to try a sample of these in the field. And it helps us to go through and manage that. And then the other one is planning for new technologies. How do we want to go through and implement new technologies and all of that? So a number of the questions that I've seen pop up here in some are all around how do you build a digital twin? And this is just from one of our other ones. We have a couple of other remote control series that go into this in a deep dive, but I'll just give you some real quick points to help you get started. Okay, establish a data environment. You need data to collect it. You need to be able to be there. I've shared a little bit about how we're creating and working with organizations to get some of the virtual models or components already there. So as we do a model of a campus, we're now creating standards around how do we've created ontology models and data models and taxonomies for different things related to buildings, water systems, wastewater systems, energy distribution networks. We've been creating the common language to help us go through and define each one of those so that it creates ways that different organizations can share what they've learned with other organizations. That helps to accelerate step 1 and step 2. Establish the data environment, build the virtual model. The third, you start creating the behavioral agents. In your environment, how do your customers work? How does your system work? Those are some of the things that you then program into your behavioral agents in your simulation environment. Again, we're working with research labs at universities to create more and more of these agents so that we have them. So they're, again, libraries of agents that you can attach, similar to creating your own SimCity and getting your SimCity up to the point where it looks like your own city. And then the last is, once you've got that, now you've got your digital twin. You can use your GIS drawings, your AutoCAD drawings as part of the basis to get you that simulated world of what you're working for. Okay, so starting a twin. So one of the last things we look at is start your own digital twin project. Start with a pilot. Take a neighborhood. Take a pump station. Take a distribution area. Take a certain microgrid area or a neighborhood. Start making use of it. Create that kind of environment and simulate and model those scenarios in real time to get a flavor for what you can do, and then you can scale it out. That's what we've started with some of our projects. We basically started with a building. We tried to do city scale first. It wasn't realistic, so we started to scale it down to building level, and start going through and looking at little neighborhoods first. That's easier to buy into. You can over sensor, and then you don't need to invest as much in the sensoring technology over time. With that information and that digital twin, you can then start moving into asset management life cycles and improve your decision making, and be able to get more money, more return on investment for all of the money that we're spending on our infrastructure and our maintenance programs. Okay. All right. Q&A. Let's go through. Got any questions that I can answer? I know that was a lot of material, and I want to thank my my team here for helping put all that material together. Didn't realize how much we had when I started talking, because I have so many stories over the years that I can share.
Well, thanks for that, Mark. I have one. We've got a few really good questions here. The first one is, there appears to be a ton of things that can be done, but what can't be done at this point in time?
I would say everybody has the panacea that they're thinking that autonomous control and AI is the way of the future and it should be done. I do not believe that we should be doing any sort of, and when everybody talks about it, it's not something that we should be doing in that realm today. And I would say the systems are not as sophisticated at this point in time to handle that kind of decision matrix. You always need to have your individual in here to help you analyze the 5, 10, or 15 decision scenarios to do that. That would be the one key. But what I do see is we do have the technology and the data sets coming together to allow us to use these as decision support tools.
Great. Another one here. Oh, there's so many to choose from. We might not get to all of them. We may have to send some emails out. Given that environmental factors are not 100% deterministic of an asset's current state, do you advocate maintaining multiple digital twins for an asset?
I'm not sure. So the digital twin is the virtual edition. When you're talking about the deterministic states, what you could be doing is sitting here and saying, is there different ways of turning flow rates in, or are there different ways of going through and changing, using different, say, algorithms to go through and make decisions? So I always assume that the algorithm models, like machine learning models or different ways of making decisions, are all libraries that can be applied to the virtual world. So if that's what you're thinking about in the way of changing it and having multiple versions, I assume that we always have libraries to basically use different decision-making tools to answer different questions. Hopefully that answers the question.
Great. Another one here about different use cases. So Mark is asking, has anyone used digital twins for IT networks? Not to manage the physical maintenance of the devices, but to assess the network state from a security perspective.
Now that one is an interesting one, because that was, we actually put in some questions. We were recently involved in a research day with a number of universities. And part of the questions were coming along was, how can we go through and address some of the cybersecurity issues related to using IT? One interesting part I find when we're dealing with energy and electric is that the IT system is an overlay on all of those systems. I assume we have a cybersecurity and an IT system involved and integrated in with our electric and water systems. And to look at failures of computers and control systems are things that need to be incorporated into this, including the cybersecurity. So yes, it is something that needs to be done. I'm not sure if anybody else on the call has any input on that, but it's definitely something. I think we should grab all of these questions and basically cycle back to the attendees and give some thoughts around it, because these are some really good questions and we can share more details of some of the research going on.
Yeah, I would agree, Mark, and we're coming up to the 5-minute mark here. So we'll make a note of this. We have your names. If you also have questions you'd like Mark to answer, you are free to email me when I send out my follow-up email. I'm just going to start my video here so you can see me all speaking. All right, well, thanks for your questions. I think we're going to wrap up now. Mark, if you just want to move that slide forward a little bit.
I will do that for you.
Yeah.
There we go.
Great. So just finishing up here, This is part of a series. So thank you all for joining us today. It was really great to have everyone, great to have such great questions. If you haven't already and you want to know about more events, sign up. The URL is in the chat and it's also on the screen there. You can subscribe from email updates. You can also follow us LinkedIn, Twitter, where else do we meet up? And I think they're the main ones. Someone jump in if I've got them incorrect. But we also post, thoughtful articles, insights on those channels as well. So you're welcome to follow us there. We'd love to see you. And with that, I think that's everything for now. I'm just going to take a moment to capture these questions, and I will see you all soon.
And if we've got all the comments, we will answer all the questions here to everybody that was attending so that we can go through and do it, because I think this was a great interactive session. And thank you very much, everyone, for attending.